In this video, I want to talk to you about how to both set up and interpret the regression analysis on two variables, both being the unemployment rates 2015 versus 2016. I have created a separate video that will walk you through the steps in Excel of actually calculating the regression values that are used in this video. It's just a little bit more convenient to do that and then bounce back to this one. So we gathered unemployment rates by state for 2015 and 16, and we're interested in whether there is a linear relationship between the unemployment rates for the 2 years. What do we mean by a linear relationship? If there's a relationship observed between the values, or is there really no relationship at all? So think about it this way. Just imagine that this is data from 2015, this is data from 2016. In this instance, what you're seeing is what it might look like if there's no relationship at all. And what that means is let's just say in 2016, we see a high value or a positive unemployment rate, let's say, for 2015, but very low values for 2016. In fact, they're negative here. And there doesn't seem to be any pattern of that when one's high, the other year is high, or when one's low, the other year is low, anything like that. Or maybe the opposite, when one's high, the other's always low, and when vice versa. So there's no real pattern here. And in fact, you would have a hard time figuring out how to draw a line through this data that would really explain it. And so that's what a set of data looks like when there is no relationship. Alternatively, if there is a linear relationship, then you might expect to see that something positive like this, where when one value is low, the other value is low, and when one value is high, the other tends to be high. You might see a negative one, where when one value is high, the other tends to be low, vice versa. And so this sort of obvious clustering, if you will, that you could draw a line through that would have some slope to it, that's what we mean by a linear relationship. So if we were going to draw the line, we might draw something that looks like this, and obviously the idea is that the dots sort of cluster or align around the line better than if you were to just say put a straight line through there. So imagine this. Here is the line that we've guessed, at least. I just drew one, but we guessed that this line might explain it. Here's the kind of line that would be a zero slope line, meaning that it's just a straight flat line. And so really when you're talking about a linear relationship, what you're saying is if I started measuring for any dot, the difference between basically the variation, so think of it like we're calculating a standard deviation or a variance. So if I were to take the differences between the line and a particular dot, and in this dimension, this would be the 2016 data over here. Imagine that. And so for the 2016 data, I say, okay, well, let's just say that the mean is whatever it is, right around 0. And I'm taking the distance between whatever my 2016 value is and 0. And I do that for every point. Then I'm going to be able to sum all of that, score those, sum them together, and get a standard deviation or a variance for all those points around this flat line. Now, I can then put a sloped line in there and calculate the same thing, and you can see that in many instances, the distance from my dot to the sloped line is a lot less than the distance from my dot to the flat line. And so the fact that that distance is less is evidence that maybe the sloped line is doing a better job of explaining the data than the flat line. Now, obviously, there will be exceptions that you can clearly point out where, say, this dot is a lot closer to the flat line than it is to the slope line. What you're looking for is if you were to do this for all of the dots and square them and sum all of that together, do I get a bigger number if I do that against the flat line or against the slope line? If the slope line gives me a bigger number, a smaller number, then that means that it explains more of the variance, and therefore there's less left unexplained. If the zero line gives me a smaller number, then that may suggest that maybe there's no relationship at all. So here's the actual scatter plot of the data that we have for 2015 and 2016. You can see that it looks a lot less like this is random and a lot more like maybe it follows a line, and in fact that line seems to slope up from lows at one end to highs at the other, and so that would suggest that this is a positive linear relationship. So we want to test whether it's actually a positive linear relationship. So our alternative hypothesis is that there is a positive linear relationship. Obviously, that means the null is there's not a positive linear relationship. Could be negative, could be zero. It'd be hard to believe that it's negative, so we're probably really just testing for zero here. So what we want to do then is use a regression analysis to figure this out. What the regression analysis will do is try to figure out what the line of best fit through this data is, and that would be the line that is a straight line, and when we try all the different possible lines we could fit through this data, it is the one that results in the smallest variance between each point and the line. Okay, and so that would be, we would say, is the line of best fit because it explains the most amount of variability in the data, leaving the least amount of variability still unexplained. And so I don't know why it keeps doing that, but anyway, this evaluates whether the variance of the 2016 data around that line is significantly less than the total variance. So again, easy way to think about that is if let's just say that the mean's right here and that this was the line of the mean, we could calculate the variance against this flat line, and we could calculate it again against whatever the slope line is. And if the slope line variance is less than the flat line variance, then that means that we probably have a linear relationship, and it's got a slope to it. So when we ask Excel to calculate this and you can do this graphically, and again, there's another video that you look at to see how to do this, but it comes back and basically says that it predicts a line with an intercept of 0.74, and so what that's basically saying is the 2016 observations are, on average by state, about 0.74% higher than the 2015 observations, and so that basically is saying that the unemployment rate for 2016 is higher on average than for 2015. So that's disturbing because we had thought maybe that unemployment had gone down. Then it also says that the slope of this line is about 0.817, let's call it. Well, the good news is that's positive. The bad news is it's not 1, and so not quite sure how to take that other than to say, effectively with it being lower than 1, what that means is that generally the 2016, well, it means that this line's sloping a little bit flatter, and the way to interpret that in some sense would basically be that if the data in 2016 is hot at the high end, or 2015 is at the high end, the data in 2016 is maybe not quite as high. And if we look at the data in 2015 that is at the low end of unemployment rates, there's maybe more improvement in those unemployment rates. And so having a slope of 1 would mean that the unemployment rates sort of improved evenly across all the states. What this slope suggests is that the improvement was maybe a little uneven. The states with lower unemployment rates had more improvement, and so that tilts this end of the line up. And the states with high unemployment rates had less of an increase. I guess not really an improvement in this case. So they had less of an increase in 2016, and so I guess that's good news. So bad news, it looks like maybe overall unemployment rates may have gone up, not down in 2016 by state. Good news is that there's a little bit of unevenness, and so if you were in a state with a high unemployment rate, you might actually have seen that rate drop a little bit. If you were in a state with a low unemployment rate, unfortunately, you may have actually seen your unemployment rate rise a little bit. The R square is about 76%. You see that. What R square means basically is that the line that you fit through this explains 76% of the total variability. So it only leaves 24% of it unexplained. Generally, high I squares like that suggest that the line is doing a good job of explaining the relationship, and so they add support to the idea that there really is a relationship there. Again, if we were to think about this from a hypothesis standpoint, we can't just look at the values. We have to evaluate whether they're statistically significant. So the alternative is that the slope of the line is not equal to 0. The null is that it's equal to 0. And so if the value 0, so a possible slope value of 0, lies inside the confidence interval, then we would fail to reject HO. If it lies outside of it, we could reject the null. If the p-value is greater than 0.05 on the intercept, or sorry, not on the intercept, on the slope, then we can reject HO. So those are the reasons that you would reject. If we reject HO, then we can use the sign of the intercept to state the sign of the slope. So if we reject that the slope here is equal to 0, then we can say it must be a positive slope because we're getting a parameter value that's positive. So when you run the analysis under Excel, here's the output you get. We want to focus on a few things. Again, here's our R square. That's the 76% I'm talking about. Let's talk about our what that 76% means. Basically, if you just went and calculated this, SS means the sum of squares. And so I'm taking the mean of 2016 unemployment rates, and I'm taking each individual state's unemployment rate, and I'm calculating that deviation between the observation and the mean. And I'm squaring that, and I'm just summing all those up. And if I were to do that for the 51 observations, the sum of my squares would come up to about 49.12 is what this suggests. I haven't done it, so can't verify that, but let's just say 49.12. If we calculate the amount of those same deviations, but instead of versus the mean, we do it against the predicted value for 2016 that's on this line, then the residuals only have about a value of 11. And so that leaves a value, 11.6 called, that leaves a value of 37.45 that must have been explained by the line. And so 37.45 is actually about 76% of 49.12. That's where the R square comes from. So we explained 72%. The line explains 72% of the total variation. And there you go. The other things that we wanted to look at were really related to the slope, and the slope coefficient in this case is the coefficient for the 2015 values. So it's saying if I were to take a 2015 value and try to use it to predict a 2016 value, would that matter? And what you want to focus on first is don't even look at the coefficient yet. Go over here and look at your p-values and your confidence level. Your p-value is 6.469. Scientific notation basically has 17 zeros in front of it. So p-value is practically 0. What that implies is basically that there is really no real probability that the intercept is equal to 0. That's great for us. We would have rejected the hypothesis with anything less than 5%. This is way less than 5%. And so we're going to reject the hypothesis that the intercept is zero, or excuse me, the slope is zero. And so now we'll go look at the coefficient and say, well, if it's not zero, what is it? And we would say that it's positive because we see that there's a positive coefficient here. And so we know we have a positive. We're comfortable guessing that it is at 0.81. That's no problem. Another way you could evaluate this would be to look at these two lower and upper confidence ranges and see whether zero falls inside of that. Clearly it doesn't. These are both positive. And so again, that would tell us that zero is not a possible version of the population that makes sense given the data that we've seen here. You can do the same thing with the intercept, and in fact, we see p-values that are less than 5%, not nearly as much, but also a range where there's no zero in it. So what that means is that intercept value, that sort of average change, if you will, not taking into consideration variations, the other variations from state to state, is positive. That, quite frankly, in this sense, means that all other things being equal, it looks like unemployment rates have risen over the last year. And that is the entirety of the presentation. So we would conclude that there is a positive relationship between these two. More interestingly, it seems that we're finding evidence that, in fact, that relationship suggests that on average, unemployment rates have risen over the last year from state to state. And that's it.